The first thing I want to do in this video is introduce a little more terminology related to rings. So a ring with an identity 1, where 1 is not equal to 0. So I said in the first video that we're often going to exclude the 0 ring by saying we're going to assume 1 is not equal to 0. Here's an example. So a ring with an identity 1 where 1 is not equal to 0 is called a division ring if every non-zero A in the ring has a multiplicative inverse. So what exactly does that mean? Remember, our ring doesn't have to be commutative. That means there exists a B in R such that A times B equals B times A equals 1. So really, it's not enough to check that there exists a B with A times B equals 1. You really want to make sure that both A times B equals 1 and B times A equals 1. All right, so if you have a division ring and it's commutative, it's called a field. So we'll talk about fields a lot in this course. Specifically in 206C, the focus is really on the theory of fields, and then Galois theory, which is about field extensions of the rational numbers. We won't talk about division rings so much, but I will give you at least one example. So I now want to prove a basic fact about multiplicative inverses in rings that's a lot like a corresponding fact about inverses in a group. So let's say that R is a ring that has an identity. If A in R has a multiplicative inverse, then it's unique. So this definition here for B, this is the definition for B to be a multiplicative inverse of the element A. But if there is a multiplicative inverse, then it's unique. So it's OK to say the multiplicative inverse of an element. So let's prove that. Well, even just using one of these pieces, if we have B as a multiplicative inverse of A, certainly B times A is equal to the identity 1. And if C is a multiplicative inverse of A, then certainly A times C is equal to 1. But then what happens when we take B times A times C? So B times A times C is 1 times C, so that's C. But by the associativity of the multiplication operation, B times A times C is also equal to B times A times C. And A times C is 1. So this is B times 1, which is B. So C equals B. So if you have two things that satisfy the definition that you need to be a multiplicative inverse, then they're equal. OK. So I want to introduce a little more terminology, and then we'll see some consequences of these definitions, and then we'll also see some examples of rings and how these definitions do or don't apply. So a non-zero element, A in R, is a zero divisor if there exists a non-zero element B in R such that A times B equals 0 or B times A equals 0. So we're not requiring that both A times B equals 0 and B times A equals 0. A zero divisor is just going to be you multiply one way or the other way, and you get 0. OK. Let's assume that R is a ring with an identity, 1 not equal to 0. An element U in R is a unit if there exists an element V in R such that U times V equals V times U equals 1. So what is a unit? A unit is an element that has a multiplicative inverse. So the set of all units inside a ring is going to be an important concept throughout this part of the course. So that's denoted with R cross or R star. And this is a group under multiplication. If you multiply two units, you get a unit. Every unit has a multiplicative inverse. I mean, there's an identity of this group, which is the multiplicative identity 1. And every unit has a multiplicative inverse. The operation is associative because multiplication is associative. So you can check. You can write down a full proof here, but it basically follows from what I just said. OK, so I'll pause and erase, and then we'll see some consequences of the definitions we've developed so far. And then later, we'll see some examples of rings, and we'll ask, what are the zero divisors? What are the units? now that we have this language of units, we can point out that a field is a commutative ring F with an identity 1 not equal to 0, so that the set of units in F is every non-zero element of F. Everything in F except the additive identity 0 has a multiplicative inverse. So one more definition before we move on. An integral domain is a commutative ring with an identity 1 not equal to 0 that has no zero divisors. So it's a commutative ring with unity so that for any element A, there's no non-zero element B, so that A times B equals 0 or B times A equals 0. So in the case that your ring is commutative, if there is such a B where A times B equals 0, then automatically B times A equals 0. So let me point out that you could also define the analogous concept for a ring that's not commutative, and that's just a domain, and that's just not going to come up as often for us as the commutative case. So an integral domain will be a really key concept, and you should just keep in mind that the non-commutative analog totally makes sense. All right, so let's apply some of what we've seen so far to show that a zero divisor in a ring can never be a unit. So let's say that A in a ring is a zero divisor. And we're going to suppose that it's also a unit, and then we're going to run into trouble. So what does it mean for A to be a zero divisor? It means that there's some element B in the ring that's not 0, such that A times B equals 0 or B times A equals 0. So I'm just going to suppose that we're in the first case for this argument, and you can think about what happens if we're actually in the second case. So let's suppose that A is also a unit. So what does that mean? There exists an element V in the ring such that V times A equals 1. Here, it's also true that A times V equals 1, but we're not going to need that here. And the idea is to consider the product V times A times B. Well, V times A is 1, so this is 1 times B, which is B. But by the associativity of multiplication, V times A times B is V times A times B. But A times B is 0. So this is V times 0, which we've already seen has to be 0, no matter what V is. So B equals 0, but we supposed when we defined B that B was non-zero. B is this non-zero element that you multiply A by and get 0, the thing that makes it a zero divisor. So this is a contradiction. So just to be like really precise, you should think about how you modify this argument if instead B times A equals 0. Okay, so let's prove our next basic fact about rings. Let's say that A, B, and C are elements of a ring, and A is not a zero divisor. If A times B equals A times C, then either A equals 0 or B equals C. This is a kind of cancellation law for multiplication in a ring. And it really is important here that A is not a zero divisor. So in particular, if R is an integral domain, then none of the non-zero elements are zero divisors. So that means that if A times B equals A times C, then A equals 0 or B equals C for all triples A, B, C. All right, so the proof of both of these statements, the second statement follows directly from the first. So let's say something about the proof in the first. A is not a zero divisor. Let's suppose AB equals AC. Well, let's just add negative AC to both sides. On the right-hand side, we'll get 0. On the left-hand side, we'll get AB minus AC, or plus negative AC. And this is A times B minus C, or if you like, A times B plus negative C. And this is 0. So A is not a zero divisor. So if A times something equals 0, that something can't be non-zero. So, A is not a zero divisor. So there are two cases. A can be 0. 0 is not a zero divisor. But if A is a non-zero element, then there's nothing you can multiply A by and get 0 except 0. So what does this say? there are two cases. Either A is 0 or B minus C is 0. And if B minus C is 0, that means B is equal to C. OK, so I'll pause and erase, and we'll see a nice corollary of this fact that's one of these classic exam problems. Let's use this proposition now to prove that a finite integral domain is a field. So what are we proving? Remember, an integral domain is a commutative ring R with an identity 1 not equal to 0 that has no zero divisors. So what are we proving? We're proving that if you have no zero divisors and you're finite, then automatically every non-zero element is a unit. All right, so let's suppose that R is a finite integral domain and A in R is a non-zero element. If we can show that A is a unit, we'll be done, because all we want to do is show that every non-zero element is a unit. So by cancellation, that is this proposition here that says that if A times B equals A times C, then either A is 0 or B equals C. So by cancellation, the map that takes any x in the ring to A times x is injective. Because if A times x equals A times y, A is not 0. So that means that x equals y. OK, but now we have an injective map from R to R. So that's an injective map between two finite sets of the same size. That is the finite size of R. So that injective map, just by counting, is automatically surjective. So what does that mean? There exists a B in R such that A times B equals 1, because something is mapped to 1 by this map. So that says that A is a unit. A times B equals 1. Because it's an integral domain, B times A automatically also equals 1. Therefore, R is a field. So this is a problem that comes up fairly frequently, so you should remember this argument. I want to contrast this with something called Vetterbern's theorem, which says that a finite division ring is a field. So finite integral domain is a field. This follows pretty directly from this proposition that says when A times B equals A times C in an integral domain. This corollary is pretty straightforward once you remember this proposition. Vetterbern's theorem sounds similar, but is significantly harder, and we're not going to prove that in this class. So what this is saying is a finite division ring is a field. Remember, a division ring is a ring not necessarily commutative that has an identity 1 not equal to 0, and every non-zero element has a multiplicative inverse. So if you're a finite division ring, commutativity follows automatically, but the argument is not easy.